Does that make sense? All right. So the next closest edge is? I'm going to make somebody say it.
C.
Thanks. Next?
C.
C.
O. C. D.
Cool. All right. So that's pretty simple. Let's contrast that with particles. So take a second to write that down, because I'm just going to erase some stuff on the board on top of it. If you would like. And I'm not building this because I feel like this is simple enough that we don't need to go through a detailed example. If you guys are okay with that. I was planning on it, but it just feels pretty elementary, so. But if you get confused, let me know. Let's convert it. I'm going to talk about Kruskal's now. And let's just not even do that, because that's... So anybody want to lead me through what Kruskal might do? So the first thing we do is we sort the edges. Sort the edges, and then the idea is that you want to do a similar process, but you want to consider all of the edges. So we're going to start with Kruskal's. Okay. Next one up. Sorry? Yes. And then, yeah. So they find the same tree. The only difference is how they build it. And it doesn't always have an important consequence, but it's important to think about when you're designing algorithms, whether you want to focus on the edges or the vertices, because they can have a massive consequence for the applications you're designing. When you're doing an exhaustive search for the optimal, it doesn't make too much of a difference, but sometimes you just want to cut off your search when you get close. So sometimes something like Kruskal's, where you're focusing on the edges, actually causes more of a problem, because you're jumping around your graph exploring edges, when really you want to find a path of some kind, whereas something that's structured more like prims is better, because you're going to be following a path and building that. And something like prims is also the sort of basis in the logic for algorithms like Dirkshire algorithms, where you actually build a path, where you're building a path to a destination. You guys ready for the fun part? Because this is all just lead up to the cool stuff where we consider whether or not it actually works. So now we're going to consider the fun part. Do you have any questions about the setup though? Yeah. All right, so let's talk about Kruskal's algorithm. So we're going to consider whether or not this algorithm is actually correct. We have the same setup as before. so I'm not going to rewrite it. The same set of V and E's with the same indexes and the same graph definition. So first I'm going to lay out an algorithm, and then we're going to sort of contemplate it. So the algorithm is, first you have to initialize. And we're going to say that our set E is assigned to, so I'm going to use this funky notation again, where I say that we sort a set by the weights of the edges. By which, all I mean is that if we have E equals E1, EJ, say, to EM, that it's sorted by, or sorted such that yeah. Oh, wait a second. So run out of space. We then take a moment to initialize our choice set. And to start our main loop. We are going to set two edges, U and V, equal to the edge, EJ. That's actually if U. These U's and V's are the worst. Okay, so that's our basic algorithm. Is there any questions about that? It's pretty simple.
Isn't it typically formulated in terms of sets, not like there's no path between U and Z?
We could do it that way. I mean, what do you mean completely formulated?
Because like Crusoe's algorithm is just short set ADT. I think that's kind of
It's true, yeah. But I mean, if we're going to talk about it in like a sort of like a heuristic sort of, I guess, what do you call it? Like a pseudocode way?
Higher level.
Say what?
Higher level.
High or low? Yeah, so you basically, what effectively we're doing is looking for the connection of a path. And if you don't find it, then you pop that edge in.
Right.
Yeah. Yeah. I mean, there's a pretty good, I actually really like the text for digging into the, you know what I mean, operational. I find the text a weird blend of natural language and proofs.
Right.
Yeah.
Well, I mean, like it's like implicitly implied when you're using this sort of set.
Say what?
Like it's implicitly implied when you're using this sort of set that that's what you're doing. So does it really matter?
Yeah, exactly. And it's just, it can be difficult sometimes to explain the idea of an The emphasis of sort of our explorations are really on sometimes what things are doing and clarity of proofs. If the language you're using is cumbersome, it doesn't express the main idea, and it can be difficult to reason about what the algorithm is doing, then it's always good to set up language and notation that reflects what the algorithm actually does, so that you can reason about it in proofs really well. So that's kind of like definitely a main goal. So if we want to explore the algorithm, the general idea is that, just like before, the algorithm I don't know if we have, we'll use TM. Yeah. So the general idea is that we're going to consider the building of the set from T1 all the way to T to some sort of ending point TM. And we're going to use the same idea of a promising structure. The idea that as we're forming this subset and we're slowly adding edges, and they slowly form together into groups. The idea that as this set is forming, that it's approaching or is a subset of some promising greater set T star. So if we write this idea out, we're going to take M. Actually, we'll use MST as a proper word to be the family of all minimum spanning trees. Specifically, we're going to consider a specific member of MST such that as a minimum spanning tree. Does that make sense? Just setting up a little bit of language. I possibly, like if this is confusing, we can switch it out. But we're just calling that a set of sets or a family of sets. And each T star within that is an optimal or potential optimal. I'm going to do it for time. Okay. So, the general idea is to show that T1, TM are members of some as they're being constructed. Specifically, using the same promising argument from our previous proof, we'll say that, more formally, we'll say that if there exists a T star in MST such that our Ti is a subset of T star, and then if we take all the remaining edges in the graph, and Ti is promising.
Actually,
Yeah. So specifically, the general idea is if we take where Ti is and we union it with the remaining elements on the way to some sort of optimal set T, that Ti, that the set we're building is promising, or that it is a set that is within the optimal set of the family of the optimal sets. And specifically what we're doing with the time indexes is indicating that there are edges that are yet to be considered. Does that sort of make sense?
that notation's a little bit unclear to me. Like, so Ti is a subset of T star, which is in.
Yeah, it's in the union of Ti. So the set T.
Or is it T star is just like
Yeah, so it's a subset of basically Ti plus the remaining elements
okay.
in the sequence towards something that forms an MST. Or
So we're okay. So it's like T star is in.
yeah,
Like could you like wrap parentheses around the
I could do we could do something like this.
Okay.
So Ti is a subset of this optimal set,
Okay.
of this potential optimal set.
And it's in. Okay,
And
yeah.
the potential optimal set can be defined as Ti plus the remaining elements to be considered by the algorithm as we're iterating.
Right.
So there's going to be a set, so these, maybe that's the confusion. These are edges to be considered. They haven't been considered yet. So these are the edges to be considered by the algorithm. This is the set we built up to this point. So we're saying that the optimal set is a subset of everything we've built so far, plus all the places we could go. So it means that T is a subset. So we haven't built it yet. We're betting that there's going to be a bunch of these, and we're going to get there at some point, potentially. So it's promising, but we know that what we built so far at iteration I is still a subset of optimal, and that the Ti is still in the family of the sets defined by where we're going.
Yeah.
Does that make sense? Did that clarify? Is it super confusing? So maybe I'll work a little, I feel like that part is a little confusing. So we're building a graph. And say that there are, let's just say that there's one MST, to be simple. So this is the MST. We've included this one. So this is our Ti, right? This whole thing potentially is our T star. Right? And there's more edges too. Right? And, and T star is in So it's not, this edge is not included. So T star is if we kind of grab all these edges, we call these edges, say, E next. I'm just kind of making stuff up right now for clarity. So we're saying T star is in our TI, where we are, union with our E next. Is that clear?
Like, it just, like, when you wrote it out, it just looked like you're saying key I is in, like, you know what I mean? 'Cause, like,
Yeah, I know the notation, sorry, yeah, I could
That's,
say
yeah,
that.
that was what I was asking about.
Yeah. Okay, cool. But it makes sense?
So, yeah, it's-
Yeah, okay, sweet. So that's our that's our goal, is to prove that that's our inductive hypothesis, is that doesn't change. That as we're running Kruskal's algorithm, that as we're running it, the fact that that where we're going, this set's going to shrink as well as we consider all the elements. That Ti is going to grow, and eventually it's going to turn into some T star is defined by Ti solely, and that's the goal, or so we think. So yeah, so let's set up a loop invariant. It's just that we're going to say that whatever I we're at is promising. Let's set up a base case. And let's consider T0 is empty. Is that trivially promising to everyone? The idea that a future set containing all the edges is promising? You know what? I'm going to specify it a little bit more than that. I'm going to say TO is a subset of every T star. Yeah. And the set of future edges is all the edges. Let's see here. I feel as though, yeah, let's take a quick, like, 5-10 minute break, or 10-minute break, and then we'll continue with the proof. I just want to give you guys a breather before.